As Desmond mentioned, I'm the CTO of VersusSystems.com. As he mentioned earlier, we use Elixir at Versus in interesting ways to make video games more fun. And a lot of what we do use state inside of our applications, which is one of the reasons why we went to Elixir, actually. We used to be on Ruby. Everything was stateless, everything was in the Postgres database, and that just didn't work. We couldn't wait that long to get our data back all the time, so we made it closer. We put it inside the application. So I'm going to talk about some of the different options that we've got. So why might you want state to live inside of your application? There's a number of reasons. For us, we needed faster access to the data that we use most often. We need to be able to answer these requests very quickly, and you've all seen like these Elixir applications that can, if they're not doing anything like talking to a Postgres database, they can answer extremely quickly, in little tiny microseconds, and it's really cool. But if you have to talk to external systems and Postgres databases, that's a little harder. You may not actually need your data to live outside of the application. Maybe it's short-lived. Maybe you don't need it to live for a super long time. In our examples today, we're going to use a session object and talk about sessions and how we might track those. All of the examples, the code examples, they're kind of simplified, so I just want to make sure that you understand that they all work, but I wouldn't recommend doing the exact examples actually in your production system. Try and make it a little more robust and exciting. The session structure that we're going to use is also very basic. It's got an ID, a name, a location, and what time the session started at. And that's going to be uniform on the data no matter which option we're looking at. The first one we're going to talk about is the GenServer-based solution. So we use GenServers a lot in our application right now. The way a GenServer keeps state is it's got this message queue of inbox of messages that come in. And every message that it processes it in the receive loop, it will take that message, take the current state of the GenServer, pass it through to whatever handler function you have, and then out comes the other side, possibly a reply if it was needed, and then also the new state of the GenServer. The state may not have changed, but that's okay. It always gets the new state, and that's what's going to be the state of that process. And that works great. And we have our session module that we have a start on here. We'll take a name and a location, and then we'll just build one of these session structs. We're just going to generate an ID. We're going to timestamp it with right now, and then we'll call our GenServer and say, hey, please store this session for me. And the fetch will simply take an ID, and it's going to return the session that has that ID. And stop will remove that session from the system. The GenServer itself, the code is actually fairly straightforward and simple. The state for our GenServer is simply a map. It makes sense for this example. So when we store the session into the system, we take the ID of that session and we use it as the key in our map. And we just produce a state that is the new version of that map, now with this extra session inside of it. Fetch, it simply does a get on that map. If it's not there, it'll be nil, and that's fine. We just don't have that session. And the remove command that we sent on the stop function is simply going to remove it out of the map, just delete it straight out of the map. And that's all we need for our GenServer solution. It's super simple to set up. It's fast. It's well known. There's a bazillion examples out there. I'm sure you've all read blog posts about it. If you go on to the Elixir docs on the Elixir homepage, it's got a whole section on here's how you can make a GenServer, and it's super easy. And it does basically the same thing. They create a little key value store, and it shows you how to do exactly that. But there's some downsides. It's limited to a single node. So that GenServer has to live on a node somewhere. If you have a multi-node system, the other nodes can access it. We can ask a different node, please give me this information from this GenServer, but it still has to live somewhere. And if that node goes away, that data goes away as well, and other nodes can't talk to it and get that data. It can also be a performance bottleneck because that receive loop is processing those messages one at a time. And and that means for every read and for every write, you have to wait for your turn. If it's heavy volume, that could end up being a bottleneck there. And there's no permanence, as I mentioned. If it dies, it goes away. So we can actually see that in here right now. So that came up, yeah. So we're gonna just do a quick alias here. And then we're going to create a new session for Phil Connors in Punxsutawney. And we get back a session object, and we can then use that however we want. And we can easily get it back out. We can do session.fetch, and we'll just copy the ID that it got. And we get back that same struct that we had in there. Super straightforward. Session.stop, give it that ID again. It says, OK, sure, I did that. If we fetch, it's gone. Everything works great. And if we create it back again, he comes back and creates a new session. If we kill our node and go back in, then we may have a small problem, because now we grab our session ID from the last one that we made, and we'll just fetch that out. And it's not there, it's gone. So we definitely lost all of that state. It just went away when the node died. And the node doesn't have to completely die. That was just the quickest and easiest way I could do that. The actual GenServer process could die, and the supervisor may start it back up again, but the data's still gone. There's ways around that. You can pull the data back in if you're storing it in some other location, like maybe you're backing it all up into Postgres or somewhere else, but then you have to wait for that to come back in, and it can be a bit of a pain. So there's other solutions. We can use ETS. And ETS can help us address some of the problems that we have. ETS provides a key value store, which is basically what we were doing anyway with our GenServer. The ETS table itself you need a reference to it somewhere. And so what we tend to do is we'll create a GenServer that will just hold that reference. That's all it does. It doesn't do anything else. It just holds the reference so that the ETS table doesn't go away out from under us. And then we can access it through the ETS module that Erlang provides. So here we just do some basic setup. This is in the GenServer that's going to hold that reference. And we just create a new ETS table when it initializes. We give it the name of the table, which is going to be session store, and we give it some table options. We're going to set it up as a set. You can also do a bag, which lets you have multiple values under the key. And you can make it public, which is what we want to do so that we can get that read concurrency. We set read concurrency true. So now any process in the system can ask this ETS table for data, and they can get it, and they don't have to wait their turn to get that, to read that data out. The actual session module itself is going to look very similar to the other one. We're just going to use ETS instead. So now we're on start. We'll take that name and location, create the struct, and then we'll call insert on the ETS module, and we tell it what table, which is just our sessions table, and we're going to give it a tuple, the key and the value. Tuples can actually, you can store any size tuple you want in there, but for our purposes, we're just going to do a key and then some value that we're going to put in there. And we'll return the session back out. Our fetch will do a lookup on the table with that ID, and because we set it up as a set, that means our answer is always going to be a list of either 1 or none. So if it found it, the list will have one tuple in it, and it will be the key value pair that we had put in there. And if it doesn't find it, it will be an empty list. So we'll return the session or we'll return nil. Stop will simply tell ETS to delete that record out of the ETS table by giving it that ID. We do a lot of this in our system as well. So there's a lot of data where we need to be able to have processes concurrently read the data, but they don't necessarily need to own full control over it. We do a little bit of both, depending on what the purpose in our system is. Again, the pros, it's fast. This time we get non-blocking reads, which is awesome, but we still have some of these same cons. It's limited to a single node. In this case, it's a little bit trickier even because the GenServer, we can at least talk to that process across nodes. It's got an ID. This ETS table, we have to create some kind of mechanism to talk to it or spawn an RPC call or something like that in order to talk to the ETS table that's on another node. And again, there's no permanence. We see that same problem out there. I also listed on here a con being that it uses Erlang because this is an Elixir conference and a lot of folks like to program only in Elixir. They don't like the idea of mixing in Erlang into their code. It's fairly simple to do. You saw the code on there. We just referenced the ETS module, but you're still having to read Erlang documentation. You're still having to understand how that works and how it interops. And for some people, that's a problem. I don't actually think it's that big of a con. I think it's good to understand how your system works, and I encourage everyone who is kind of on the fence there to dive in a little bit and look at some Erlang. The example is going to be very similar, actually. So this time we're going to alias a different session, and we'll still create fill another session. We'll get a brand new session back, and we'll copy our ID, and whoops, session.fetch with that ID, and we get our session back. I won't show you the stop again. It's basically, it'll do the same thing as before, but again, we don't have our permanence. If I kill that node, and I go back in, and I alias that up, and I say session.fetch, and I use that ID, it's gone again. And so now we have a problem. Again, there's ways around this. You can, when it starts back up again, you can always rehydrate that state from somewhere as long as you're storing it somewhere else as well. But then you have to remember to store it somewhere else. And you have to wait for it to come back from wherever it is, and that can be a big problem as well. And we've run into that and fought over that, and how do we handle this, and what happens when the node takes minutes to come back up because it's trying to get all this data in there, and it can be somewhat frustrating. So now I want to jump over and talk about Amnesia, which is kind of the point of this talk. And it was billed as something a little bit different, so I do want to apologize. I billed this as talking about the Amnesia Elixir wrapper because my initial thought and expectation was that, hey, there's this cool library out there and it'll make the Elixir folks happy because they're seeing Elixir and it's not Erlang. However, in figuring out how to use Amnesia and the Amnesia library, what I found is the documentation on the Amnesia library is lacking. It could be improved. The README is kind of nice. It's got some great examples, which is why I thought it would be a cool library to use. But as soon as I wanted to actually do more than whatever was in the README, all of the docs, almost everyone literally says, go see the Erlang Amnesia documentation to understand how this works. And I was like, okay, so I might as well just go read the Amnesia documentation. And so I did. I dove in and I read the Amnesia documentation, which is actually really good. The docs on the Erlang libraries, in my opinion, are just as good as the documentation that are on all the Elixir libraries. They're very big on documentation on that site as well as on the Elixir site. So there wasn't a whole lot, maybe not even any, on the Elixir site about Amnesia. There is stuff about ETS on there, but to look at Amnesia, I definitely recommend going over to the Erlang docs and reading through those. They're very robust documentation, and I learned all about Amnesia on there. I will caveat, we aren't using it yet. So the plan is soon to start migrating our systems to use Amnesia to solve some of the problems that we're running into. But I have high hopes that it's going to help us get through some of our near-term bottlenecks that we see out there. So what is Amnesia? It's a distributed management database system. So it's actually having a real database inside of your Erlang application or your Elixir application. And it is fault tolerant through replication across nodes. It's a fast key value lookup. So it's not a SQL database inside of your application, but it is a key value database. and it distributes data across RAM, disk, or both. And you can even reconfigure it dynamically while the system's running. You don't have to tear your system down to like migrate your data around, change how the structure of your tables are. You can even change the replication if you want to add a new node and replicate all the data to that. It's super easy. You just spin up the new node, you tell Amnesia, hey, there's a new node that needs this data, and it just copies it over there and everything's great. And it does allow you to do some more complicated queries. There are query modules that are optional to use, and you can use those if you want. I'm not going to go into those in this talk. I think there's a whole other talk I could probably go into that's actually deep dives into Amnesia a little bit more about how it can actually be used. I wanted to kind of use this talk to show how you can use Amnesia in contrast to some of those other options that were out there. So if you set up a multi-node system, then what you can do is choose to store your Amnesia tables in memory or on disk or in both. All of our examples, we're going to do it on both. I find that's the most useful. If it's just in memory, I feel like you don't get a whole lot over just using ETS, and other than you do get the replication, which is nice, but by using it on disk, you can also make sure that you don't lose anything if your system goes down. You don't forget your history. The other difference is Amnesia, because it is an Erlang system, it uses records. And so we're not going to be using structs. There are ways that you can easily turn a record into a struct, and you can turn a struct back into a record. But for these examples, we're going to keep it simple and just use records. Elixir gives you a way to easily define an Erlang record. In this case, we're defining a record that's called session, and it's got the same data points that we had on the other one. So it's got ID, name, location, and started at. We've got to do some setup. So this is a one-time thing. When you want to start using Amnesia, you have to create a schema. So if you haven't created a schema yet, by default, you get one automatically. If you kind of just start it up, you'll get a RAM setup, but we want to use the memory and disk option. So the first thing we're going to do is run this function that is going to be called create schema, and it's going to check to see, hey, do I already have one? Just a little protection there in case someone runs it after we've already set it up. And if we don't, we're going to map over all the other nodes in the system and tell it to please stop Amnesia. We're going to stop our Amnesia on our current node, and then we'll create the schema and tell it to use all the nodes in our system. And then we'll start Amnesia back up on our current node, and then we'll go over all the nodes in our system and start up Amnesia on those as well. With a schema in place, now you can create a table. So we just are going to have the one table for this example. Again, we have a little protection. If the table exists, we don't want to try and create the table all over again. If it doesn't exist, then we'll use the create table function that Amnesia gives you, and we'll create a table that's called session. You can use a different name than your record's name, but by default, it kind of expects those to be the same. If you want them to be different, you have to use an additional option in the definition of your table. And we're going to tell it our attributes are all of the fields that are on that session record. And disk copies is the definition of where you want to have it replicated in both memory and disk. So it's disk copies because it's in both. It's in memory, which is default, and on the disk. And we're going to tell it all of the nodes where we want that to be. And so we're just going to give it a list of all of our nodes in the system. I also made a quick little utility. The base way to use Amnesia is via transactions. It is a database system. It's designed to be robust, and it uses transactions to ensure things happen. And so you create a transaction and then execute a function. All of these are super simple transactions. They are full transactions, though. So you can put a function that does any number of things. You could read out a bunch of data. You could mutate it. You could write it back in all in one transaction. And if it fails, it doesn't happen because it was a transaction, and it'll roll back and everything will be great. These are just super simple. We have a read one, a write one, and a delete. And we're just basically wrapping what Amnesia is doing but just automatically creating a transaction for this. Again, I just wanted to keep these examples simple here. And then our start function, again, is going to take a name and a location. This time, though, we're going to create a session record instead of a struct because we're using records. The same data format, though, is there. And then we're going to use the write function that I just showed you to write that into our Amnesia. And the fetch function is going to take an ID, just like the other ones did. This time, we're going to read from there with that session ID as the key. And we're going to get back a tuple. And the tuple is going to say atomic, and then a list with all of the sessions that are under that key. We're using a set type, which is the default. So you didn't see that in the table definition because it's the default. But you can also choose to use a bag, just like ETS lets you do. And since it's a set, though, we're either going to get a list of 1 or we're going to get a list of none. And so we're going to return the session, or we will return nil. For stop, we're going to just ask it to please delete this session out of the Amnesia table. So the pros now this time are it's fast. It can be just as fast as the other solutions because you're operating on memory. I didn't mention it earlier with the transactions, but you can choose to do dirty operations if you want. So you can run all of your writes through transactions if you wanted, but if you wanted to do reads and not have to worry and make sure you get them as fast as possible, you can do a dirty read, which will just go straight off of the memory and it won't do any verifications or wrap it in a transaction or anything. You get permanence across restarts by using the disk copy option, and you can scale it out over any number of nodes within reason. I think Miriam pointed out a number of reasons earlier why things don't always scale as you would like. The cons, I only have the one up here this time. It's the same one that was on ETS, and that's that it uses Erlang. If you want to avoid that, there is a library, Amnesia. It is, as it turns out, a pretty light wrapper over Amnesia because you have to understand Amnesia in order to use it. But it does give you the more Elixir type interface onto it. And I'm sure there probably are some other cons, but as I mentioned, we aren't using it yet, so I haven't found them. So in all of my testing and playing around and spiking examples, I haven't found any cons yet. It actually works and solves all of our problems that we currently have. And so I fully expect we'll probably get some brand new problems that we don't know about yet, and we'll have to learn how to get past those. But as of right now, there aren't any problems with the system. Everything is super happy, and it all works. So let's take a look at some of the things that you can do there. So I've been showing you just this one console here, but I do have a second tab where there's another console at play. So this is in2, and we've got in1 over here. I've been working on in1. In2 is another node on the same cluster. If we do node.list, you can see it sees in2 over there. It's all set up for us. If we alias Amnesia session.session, now we can play around, and I'm going to go ahead and still fill another session here. And this time we can do some interesting things, more interesting things than last time. So now we'll take that ID, and we can do session.fetch with that ID. And we can get our session back just like we could before. That's awesome. But now if we flip over to node 2, we can do session.fetch. And we get our record back there too, which is awesome because I didn't even have to do anything special. I didn't have to tell node 2 to do anything. I didn't have to make sure that there were messages. Node 2 didn't have to ask in a special way. It ran the exact same command, and it got the exact same data back, which is super slick. And you can also, of course, stop that same session. And just as you would expect, if we go over to node 2, and actually I'll just do the fetch again. It's not there on node 2 anymore either. It's across the board, as you would expect. It works across all the nodes in the system. And I just have the 2 nodes, but you can keep adding more in and it'll work just fine. just as you would hope. And now I'm going to do something even cooler, because now if I kill node 2, node 2 is not running anymore. I go back over to node 1, and this time I'm going to make a session for Ned Ryerson, create him a session up, and we'll go ahead and copy his ID. Whoops. And we'll go back over to this, and we'll start up another node 2 again. So node 2 is firing back up, and we'll do our alias again and do session.fetch with Ned's session ID, and Ned comes right up here. So even though node 2 was down, we were writing into the system on node 1, node 2 came back up, and it just still has full access to everything that happened while it was down. It doesn't matter. It will, I mean, there will be performance penalties if node 2 is down for a long time and gets way out of sync, because it'll have to get back into sync when it comes back up. But assuming that you have a reasonable operation system, that if node 2 goes down, node 2 doesn't have to stay down very long. When it comes back up, it will get back to a solid state very quickly. And it doesn't matter if all the nodes go down in the system. We can also kill node 2. We can go back here and we can kill node 1. We'll fire node 1 back up. We'll fire node 2 back up. And I guess if I want to do that, session.fetch. And Ned's still there, session's still there. We killed all of our nodes, we brought them back up, and we still remember all the things, and we don't have to worry about where are we going to bring stuff back again. You may still want external storage. You may want to send things out when you're done with it. For our sessions, when we're done with them, we would want to remember that someone had a session, so we can record that in long-term, like Postgres if we wanted to, and delete it out of our in-memory state that we don't need anymore now that the session's over. But it's a pretty flexible system, and that is the end of all my examples. And for more information, the Erlang docs, as I mentioned, go through those. There's excellent stuff up there. That's my GitHub. I'm going to put the code examples that I had in here, as well as these slides, in a project on there. And that's my Twitter. I will tweet out the exact location of the code and slides. So if you want to actually look at any of those, you can. And I think that's about it for my time.